this lecture again is one where I'm making it up as I go along because I've got to release a game in 7 days, so I don't have time to write a lecture. But I've got plenty of material to work with. Okay, so this is okay. We'll start from the other scene. Save, yes. Okay, I decided we'd done enough in 2D. We've done 2D almost the entire course, right? And we've not really covered on 3D. So we're going to talk about some topics in 3D that I think are pretty interesting. Oh, I've not shared screen, have I? There we go. Right, so this is a game prototype I made a while ago, right? And there's a bunch of stuff we can glean from it. And we're going to go into them. We're basically going to cover stuff that we never covered in 2D and then cover them in 3D. Right, so one of the things... I'm getting a bunch of errors, but that's fine. Okay, let's start with the first thing that I wanted to do. I just wanted to talk about some practical uses of dots and crosses. Okay, in fact, I'm going to make the game screen bigger. No, can I do it like that? Whoop. Okay, let me, I should probably make it 16:9 and then restart it because it calculates the CRT vibes based on how big the screen is. So, first of all, you've seen I've got this object in my hand that I'm throwing around, and it's like, it's some quantum zoom device, right? Not like Zoom calls, but you know, I can do that, and I can zoom. I can wall jump. And by the way, at any point in this thing, if you're seeing something and you're like, oh, how did Alex do that? Feel free to just shout out, because this is a completely unplanned lecture, so if there's something you see here and you're like, maybe you're like, oh, how does he get the rain to run down the screen or something? Then you can, like, you can just ask me, like, hey, Alex, can you explain that? And I'll explain it. Anyway, the first thing I want to show you is, we've talked about cross products before. Let me just show you what happens when I throw, let's say, a grenade. I hope you can see this thing. It's just using a little triangle mesh, right? Okay, well, that thing exploded everywhere. But you see when I throw it, it spins, right? Are you seeing that? Like, if you imagine I throw right up, we've originally got a triangle, a pyramid like this, and it's gonna flip in this direction. It's gonna flip down. Watch, see that? It's basically got top spin. And now I believe if I throw it this way, I might even get bottom spin. Let's go this way so you can't see. Okay. Or if I throw straight forward, do I get any spin? Okay. So how I'm doing that is, okay, and this is a good example of, let me get Discord out of the way. This is a good example of a good use of cross products that you might want. I've got this class called throw, right? And it's when I've got an object, I can throw it, right? It will launch it. It grabs the thrown object. It gives it a velocity based on on the camera's forward, right? So forward from the camera. So to make things clear, the camera is detached from the player. So I have a collider, obviously, but when I look up, my whole collider doesn't tilt, just the camera. Because it would be stupid if the collider tilted with me. Okay? So, in fact, better to show than to say. See if I can find where I am. There's me. Okay. And do you see when I'm tilting, you can see the camera going up and down and the item, but my actual collider, this plane, is not actually tilting up and down, just the camera. Okay, so there's two interesting variables we have. We have the player forward, okay, which I can use to give motion. So if I move, if I move the player in the player's forward, right, then I'll go forward and backwards like that. And if I move the player left and right, I'll go like that. But then there's the camera forward, which is based on my angle, right? So when I throw things, obviously I want to base it on the camera forward, you see? Right? So you can see here that whenever we throw an object, we get the object's velocity is the camera forward times 13 plus my velocity, because obviously also when I run, I want it to inherit my velocity with Galilean relativity, right? Or if I'm falling, I want it to fall with me. Otherwise, when I run forward, or I'm falling and I look down, it might go behind me, right? If I'm falling faster than I throw it. So it should always take my velocity and add this. Wait, am I recording? Yeah, I'm recording. Am I recording that? Yeah, I am. Okay. And then, right, then we have angular velocity, right? So we can... This is interesting. There's this thing called angvel, which I'm not even sure is actually used. The ring magnitude. Okay, oh, sorry. So that's my angular velocity, right? So what it's then going to do is it's checking my RVX and RVY. RVX is my right stick's velocity of X and my right stick's velocity of right. In other words, it's how fast I'm spinning in the game. So, this is a low angular velocity, right, and this is a high angular velocity. Right, and it's the same in Y, right? Like, that's low, that's high. Okay? And then we've got... So then we can grab the magnitude of the angular velocity to check how fast I'm spinning. Right? And then... What's going on here? We've got the velocity plus equals the time dot vector time times the cross of the item forward times the z distance. Okay, so I think that this line of code... Whoa, look, I clicked the rain. Let's not click that. Yeah, this line of code is just making it that if I spin, it will... Why can't I shoot anymore? Okay, when I spin, there'll be some kind of spin on the object as well. Okay, but this is the important line. So if you want to see that line of code, what I've done is I've crossed my angular velocity with the items forward. So if I'm spinning left and it gets the items forward, right, then you've got, remember, direction 1 would be left, direction 2 would be forward, so it would apply a spin that way, right? So it'd apply a top spin of some kind. Right, or like it would add a velocity upwards slightly, but this is the important one that I want to show you, right? I'm gonna comment this line of code out, and you just see for yourself, and then we'll go through the line of code, because maybe I'm not making it clear like what's going on here. Oh, I've moved away from my hotspot. That's annoying. This one takes a bit longer to load than the old demos. So, right. Watch when I throw now. Have you noticed how this thing is no longer spinning? Right, I just throw it in a direction, and it's just, it's being a triangle. Is it clear what I'm talking about? Right. So, it doesn't look that good, because it doesn't look realistic that this thing would be flying through the air, and it just perfectly moves up, and then, it just perfectly slides. I actually wanted it to have no friction and slide a lot, because it's more fun as a game mechanic, but, it just looks a bit weird, right? Now, what I'm doing here is I'm making the angular velocity. First of all, I'm getting its velocity, you know, how fast we're throwing it, times some random factor, right? And then we're crossing its velocity, aka the camera's forward, right, normalized, and, well, plus whatever this is, and my transform.forward. Okay, so we're taking the cross product, if I've got my player here, right, and then the camera's like here, we're taking the cross product of that, the forward where I'm facing, if those are my eyes, right, well I suppose my eyes are here, right, and this is just more like my hands, my forward, and this thing's forward, right, and so if you've got this way, and then you're curving upwards this way, right? So, you know, you're putting your hand out that way, and then you're curling up, then that means the angular velocity is going to be that way, right? And so as you know, right, so in this case, you know, we've got this, and it's curling that way, so the thumb is coming out of the page, right? It's coming towards us. And if the thumb's coming towards the page, that means it's rotating around this axis. So it means the thumb becomes the axis of rotation. So the whole thing's going to rotate like that, right? So, which is exactly what we want. So maybe I can pause and fly to him. Oh, I need to uncomment that line of code and save and run. You gotta love this MS Paint diagram. It's really good, isn't it? Right, so I'm gonna throw it and then I'm gonna pause. Alright. Well, maybe I can do a better throw than that. You can see now it's spinning, right? So let's do it again. We'll apply a lot of spin like that. Right. Then we'll pause and we'll fly to it. Wherever it may be. Okay, here we go. Right? So the forward is here and the up is there. Right? So therefore, we're curling up that way, so the angular velocity is that way, right? In this direction. It's straight forward from where I am. And if you rotate it around straight forward from where I am, you're going to get that rotation, right? Well, I'd need to do it. Well, I can't grab it exactly. It'd be more like, you know, like that. Right? And so that's exactly what's happening. That thing's spinning around that axis there. Alright? So there's one useful use of cross products that you might want to apply. And you can apply that in all kinds of things. It might not just be throwing, you might shoot something and you want it to spin in the air. Well, if you take its angular velocity and cross the angle you fire it at with, you know, or the forward plane it's traveling in with the angle you fire it at, then you'll get a nice topspin. Right, so next thing I wanted to show you is some dot stuff. Okay. Oh, actually, I've accidentally loaded the scene we're already in. But while I'm here, we can talk about moving platforms. Okay. So I'm riding a train right now. If it ever loads. Right, and I'm going to jump off this train and onto this train. Whoop. Right. And you see that even when this train's decelerating, I'm staying on it. Everything looks all good. Right. In fact, it'll be a better demonstration if I start on the first train, because I can easily like walk off that one onto the lower one. So Let's fly into this rubbish looking tunnel. Warp player to camera. Cool. And it works when you're inside the train as well. You don't just have to be on top of it. Right. All that's happening here is it's the... Oh, I fell. Whoa, what's going on with me? Whoa! I'm rotating in a strange fashion. I've clearly, like... shouldn't have warped myself the way I warped myself. Yo. Warp. Player to camera. Ground player. Warp. I think WRG means warp, rotate, ground. I'm sorry that compilation takes so long. Okay, right. So now if I jump off here and onto here. Right. But when I jump, you see, I'm still jumping relative to this thing. Right? I'm not flying off. I don't know why my rotation is doing this right now. This is quite annoying. Oh, I know why. It's because this game takes place in like a space station, and when you go up the walls, your frame of gravity actually rotates. So, like, we're now falling in a different direction. That's why it looks really weird. But you saw that we stayed on the platform, and when we jumped relative to the train, and when we jumped on a new train, we jumped relative to that train. The way this happened is, on collision enter, right, it finds if something has a ride me on it, a class called ride me, right, and then it sets your velocity modifier to that thing's velocity. Okay, and then it also does it on stay. Right, you could also just cache the rigid body and then always just grab its velocity every frame. Then, right, first of all, when we land on it, we may want to set our actual velocity to the velocity of the thing we've landed on. I think we do that. We got crash velocity. It's somewhere in there. So first of all, you set your velocity to the velocity of the thing you're standing on, and then every frame you take your drag, and you, instead of dragging to 0, we drag to this, the effective velocity modifier, which is, I told you the whole world rotates, right? That's why this quaternion stuff exists, but you can ignore that. We're essentially using this velocity modifier, which is the thing we're standing on. So instead of dragging to 0, we drag to the velocity of the thing we're standing on, and well, hey, we've got that. Now then what you can do is, you can make it that if you jump off, after a few seconds you will lose all your velocity. So that way if you jump off a train, it's not going to feel really weird when you keep flying through the air for ages. But then when you hit the ground should become your new velocity, so 0. Right? So that's one application of what we've been doing. Now let's go into the sewer, which is going to compile faster. So we can talk about this. Which is also not done, that's why it compiles faster. Right. So, right, say these are slopes, and I'm standing on slopes, right? Typically in a game, I don't want to fall down a slope. Right, like, I want to be able to walk up the slope and just stand there. Now, this is at odds with everything we've learned in physics, because remember, we've been getting rid of friction the entire time. And if there's the only reason that we don't fall down a slope in real life is friction. Right, and balance. So, in here, we don't actually have any friction. So how is it that I'm not falling down this slope? Right? Well, the only thing that's going to pull me down this slope is gravity. So I have a little trick. It's called turn off the gravity when you're on a slope. Right? And this trick is also very useful for other things, because let's say I have a box collider. Well, we can just use this one. No, we can't. let's make a cube collider here, right? Put it on the ground. And let's say this is a fence, right? A railing. We make it really thin. Like that. Okay. I wonder if I can add a collider renderer to me, because I have a collider. It's this. If I mesh renderer, and we need a mesh filter. I don't think I'll be able to do this at this point, to be honest. Capsule. Oh. Material, just anything. Okay, I don't seem to. Oh wait, there we go. Right, we got a capsule. I'm not sure it's the right capsule, but I mean it's got a face on it, and also it seems to be bigger than me. But it'll give demonstration purposes, right? If you imagine I'm standing on top of this thing, and I have a capsule collider, then when this thing is here, can I grab this, please? Right. When it's here, oh my god. Okay, you can imagine that because I'm on the surface of a circle, right, I'm gonna slide down. Right, the expected behavior here would be that I would slide like that and then fall down. And that's really not what we want to happen when we stand on one of these surfaces, because it's going to feel bad to the player, because to them, they don't understand that they're a capsule, right? The reason we use a capsule is it's easier when you walk up the side of something, you know, the exact same reason it will scoop. If we had like if we were a cylinder, then we could just bump into the floor a lot and it would be hard to get up things. But having a sphere makes a smooth surface and it makes it easier to run up the side of things. Okay, so let's say, okay, let's get rid of this nonsense. Wait, what? This one. Right. Now look, even though I have a sphere, I have a capsule collider, so we can see. Where's my capsule? Where's my actual collider? Is it the crouch collider? Okay. It's on here somewhere. This one. Right? You can see that, you know, based on these green lines, you might not even expect me to be standing on anything right now. Right? It doesn't even look like I'm stable. And yet I am, because gravity's off. As soon as I stand on this railing, gravity's off. Right? So it doesn't matter that it's really thin. Right? I can walk along it because there's no gravity. Now you could also balance it by making its collider a bit wider than it actually looks, or by, you know, just tweaking this behavior. What I do is I turn gravity on when you input. So when you start walking, the gravity turns on again. And that's why when I'm, you know, when I'm here, it's fine. But as soon as I press something, I start falling. Right. The reason I do that is because, you know, same reason, say you're walking up a slope, you want gravity to start affecting you when you're walking down. Okay, so we can look in the code at where this is. Let's look in the gravity. Is that the wrong? Okay, and it's in here. We're just setting the velocity to 0. Or here actually. I'm pretty sure it's one of these. We just basically nuke the velocity and turn off gravity at this point. Right. Oh yeah, look, it returns. That's what happens. So it sets your velocity to whatever your velocity is with a y of 0, and then returns. Whereas normally it's going to add gravity. You know, you got v plus equals g dt. Right? where gravity direction's down. Now, I don't need that else, because it already returns. If you're grounded, I've now added this thing, right? So I'm going to show you something else. So I wrote this yesterday. Let's say you're on a slope, right? That feels okay. I mean, okay, you should definitely be able to walk up this slope, right? That looks walkable. This one, more precarious, but walkable. This one is starting to look like the limits of maybe you shouldn't be able to walk up this anymore. This one definitely, like, you shouldn't really be able to walk up this. It's a bit stupid, right? And this one is absolutely obscene. This is like some Skyrim climbing mountains on a horse type thing, right? It's like the idea that you should be able to walk up this is ridiculous. You shouldn't be able to walk up this, right? So we need a way of, if there's no friction and there's no gravity, then when you walk at something, right? Okay, let's imagine I have a really steep slope like this, and then I walk at it. Well, my velocity has a component in that direction, right? It has, you know, here it has its full component, and then here it's doing like, you know, cos of this angle. So eventually, once it gets to 90 degrees, it has no component, right? Because cos of pi over 2 is 0. But here, it's still producing some forward, right? It's still producing some up. And then so that's the resultant speed, essentially, because the rest is normalized. You know, there's a normal reaction force pushing back on the slope in sort of this direction, right? And that's going to take away most of our velocity, like everything apart from that. And then we still have some resultant force in this direction, which I guess would be, if this is V, it's going to be V cos theta sine theta, maybe? But yeah, we're going to get a really small velocity forward, right? Which we don't want, because it's ridiculous that we could walk up this slope. So what we've done is, if you look on collision enter, right, I've made, where did I define this? Ah, here we go. On collision stay, I did it, right? I've got this thing called last y normal. So the last y normal is equal to the last contact you hit, right? So your hit.contacts.normal. So now in gravity, avoid gravity, we take the last normal and then we reflect it. So we flip the y upside down. Because if you imagine, you know, you're going up this way, and then we flip the y. Right. So okay. Whoa. You've got your slope here, right? And then we've got the normal here. Because you're pushing against it, and that's the normal of the slope, obviously. Now, if you take that exact normal, or to make it more convincing, let's do it there. So we take that normal, and then we flip the y down. Okay. In fact, that's a terrible way of doing it. I really should have flipped it 90 degrees. I got lazy. But I basically, yeah, okay, my maths is wrong here. I was trying to be clever, but I'm not being clever, I'm actually being an idiot. I was essentially, 45 degrees is going to work, right? I take the normal and then I flip it that way. it would be better to cross it, and then you cross it with this direction, and you'll find the tangent to it. Okay, what I really want to find is this direction down the slope, because I want to push you that way. Right? So it's kind of what I'm doing there, but not very well. But it still works. That's the thing about physics. A lot of the time, it doesn't have to be perfect. It will just work. So then what I do is I take the magnitude, which is, okay, I dot my vector 3 dot up with the last normal, right? So I'm dotting this with that normal, okay? So when it's directly up, that means I'm on the ground. So if I have something going, if I have a collider on the floor, it's going up, and then I have me, you know, the normal is going, well, up is up, right? We're using up and the normal. If they're both straight up, then that is going to be equal to 1. Because if you dot something with itself, you get 1. Right? If it's a direction. Now, if it's horizontal, right, we're going to get a dot product of 0. So if we're, based on the direction we're getting, we'll get a dot product nearer to 1. So 1 means we're entirely vertical, 0 means we're entirely horizontal. So then what I'm doing is, I'm taking the dot product of up and there, and subtracting it from 1. So now we're getting a value of 0 here, and we're getting a value of 1 horizontally. Right? And that's going to be our magnitude of how much we push ourselves. Because when we're on a really steep slope, we're going to get a dot product nearer to 0, right? So then if you subtract that from 1, we're getting a value of 1. And 1 is the force of how much we're pushing. So when we're on the floor, we're not pushing ourselves, because 1 minus 1 is 0. Is this making sense to you? So, you know, we've got... Oh my god. Okay. Just to reiterate one more time, just in case anyone's not got it. When the plane is flat, the dot is 1. When the plane is vertical, the dot is 0. So now if you subtract this from 1 and take the absolute value, so you never get a negative. I clamped it, right? Then I should have absed it, really. But if you do 1 minus, but it doesn't matter, right? Because you're never going to be upside down, and that's the only way you're going to get negative ones. So if you've got 1 minus 1, so here this is 0 now for a magnitude, and 1 minus 0, this is 1. So it's just a way of inverting it, because we want a high magnitude when you're on a steep slope and a low magnitude on here. Then we just add it, right? So we're adding our velocity is this reflected value, which is wrong, right? Times the magnitude times 2. And what we see now is, if that's uncommented and it's saved, when I walk up a slope, right, this is fine, right? I mean, it's slowing me down a little, which is okay. I get slowed down naturally a bit as well. Right, this one's now feeling hard to climb up, but it's easy to climb down because it's pushing me down when I move. It gives me a shove. This one, okay, let's try walking up this one. Well, now I can't. Right? It's just bobbing me back. And this one, no chance. You know, I can walk at it all day, and it's not gonna... Okay, I jumped at it, and it worked. I think that's because... I do know the reason for that. The reason for that is gravity only happens when I'm grounded, and because the dot wasn't high enough on this surface, it won't ground me. So, you know, I could just remove this line of code that says if you're grounded. I just wanted it to not happen in the air. You know, you're jumping and you start getting pushed. So you'd have to have another variable that's not just grounded but push, you know, like currently touching something. So if if you're currently touching something, then this function should be running, right? And so that's, you know, and this is especially useful in third-person character controllers because, you know, if you're watching your character run up a slope, you'll want them to, like, you know, turn and run back down again. This is one of the things I did on the current game I'm working on. He had this, like, Fee, who's the main game designer, had this exact problem, and I was like, you just 1- it, mate. Right, so we have 10 minutes left. So we've done throwing, moving platforms, slopes, railings. Oh, here's one. Right, sometimes you want to crouch in a game, right? Like that. Right? Now, the problem with doing that is when you crouch, it's going to create problems. You can see the way I'm doing it is really cheap, right? I have one collider on the bottom, which is a circle, and one collider on the top, which is a sphere. And then what's happening is it just turns off the top one and remains with the bottom one. But when that happens, it will recalculate your collider, so there can be problems. Now, I found this to work. Whoa. That wasn't because I was crouching, that was because I fired my warping device, don't worry. So there is one fancy solution to this. I might actually be able to, instead of demonstrating it to you, find a tweet where I talked about this from Alex's Games Crouch. Yeah, I asked, like, hey, how does everyone do their own crouching? Right. Does he have a gif of it? Or does he not? Does he just talk about it? Because this guy, okay, it was he conceptually just described it to me, so I'll just have to describe it to you. Right. What he does in his game, which I think is quite clever, is he has two colliders sitting on top of each other. Right. Well, he kind of has like two spheres like this, right? He has one here and one here. And then he pops it up. Right, so he just pushes this up. Okay, so he's got his crouch collider, they're both on top of each other. And then when you stand up, he lerps this one up here with physics, like a snowman almost. So that way you're not going to have a problem. Like, that way now you've essentially got a new capsule collider, but, you know, en route, you're not adding any colliders, so you're not recalculating collisions. You just have, it's all based on rigid body physics. So it's gonna break class, potentially. However, the problem I see with this is that, you know, you might have something here, you might have a pole here, and now you have a collider here and a collider here, and now it's, you know, the pole is stuck in between your two colliders here. So that's why I avoided that solution. Does he? I'm pretty sure that he has some clever workaround to that. They have two colliders, one for the body and one is a riser. Top one is a pill and the bottom one is a sphere. They overlap. Depending on what you need, you might need some. Okay, so he uses a pill as well. But I'm unclear about how he's popping that up without breaking everything, but we'll see. Right, so that's one more thing. Let's see what else is on the list that I could quickly show you. Circling an object. I forgot time. Okay, we could talk about this. And if we don't finish it now, we can finish it tomorrow. So, let's say we have an object here. right? I'm now going through basically topics that other people have asked, like, Alex, help me, I don't know how to do this physics. Right. Let's say here we want to circle around this object, which is a common behavior that you might want to do in a video game, right? You have something here, especially in, like, if you're making like a Dark Souls style game, you're gonna want to spin like this, right? But the problem is, right now I'm just using the 2 sticks, right? You need to have some behavior that's going to do that. So, in order to do that, normally, right, when you press left, and you got your, that's your target here, and you want to walk around in a circle. Normally, when you press left, you move yourself left relative to the player. But here, we want to keep you in a circle. So we're going to need some centripetal force, right? So we're going to want to add an mv squared over r forward as you walk around, right? And also we're going to want to turn you, right? And then in this direction, we're going to want to do... Well, it's actually not that hard to turn you, right? Because we can just always turn you slightly towards the thing you're facing. That's not an issue. But we're going to need to add this mv squared over r. And then we're going to need to... this v, right, is not immediately clear because this isn't your velocity. It's your tangential velocity. So what we need to do is we're going to have to cross the upwards of this. So if I fly into the seam, we fly above it like this. We're going to have to cross this upwards direction, this, right, with the way towards the player, this. So we've crossed this with this, then we get this, right? So we take the cross product of this out of the page, okay, and this way, the radius, and it will give us this r, right? Or maybe in the other direction, so you have to be careful with your directionality. Then you can add a force that does mv squared over r forward, and then you'll be able to walk in a circle around. Now, I haven't prepared it, so we're not going to code it right now because we've got like 2 minutes left. But I'll prepare that for next lecture just for the start. Because when my friend and I did it in Unreal, we couldn't get it to exactly work. So you'd walk around, and when you did a full circle, there'd be a tiny bit of drift. But he really wanted it so that if you do a full 360, you will end up in the exact same place that you started, right? So I ended up coming up with a formula for him that would override this. And that brings me on to the final lesson I'm going to give you, which is estimation, which is essentially things in physics don't always work, and you can write something straight out of a textbook, but as soon as you start simulating it, it's not actually going to look like you think it's going to look like. So what we often do is we throw factors in to estimate stuff and make stuff work. One of them is the stick movement, right? Because, I can move slowly or I can move quickly, right? And it needs to feel good. Essentially, you should be able to... When I made this game, I wanted it that I could focus, much like I am now. I could focus on anything on the screen. So let's say that thing in the middle, I could turn my camera to it, or this white thing, right? Even if I'm right next to it, right close to it, I can still spin my camera so I'm facing it. Or if I'm really far away, I can spin my camera at the right speed. So I wanted it to feel like, you can always sync your sticks and spin well. But that takes some special factors, right? Because it's not enough to just turn your stick. So I'm going to show you, it's kind of like how a PID controller works. we're going to see if it comes out of this rotation. Maybe not. Maybe now that I've taught a physics course, I'll be able to get the centripetal force working a little bit better than I did when we guesstimated it. But next lesson, I'm going to basically talk about spinning around this thing and talk about guesstimation on the stick. And we'll see what else we have. Someone wanted to do water, so maybe we'll go into swimming. And then that's basically it, right? And then we finish the course. So what I want to know now is, does anyone else have anything else? Any physics problems that you would like me to solve next lecture? Because we only have one more. So speak now or forever hold your peace. And it could be anything, you know. You'd be like, Alex, I really want to know how to solve XYZ. Because I'm running out of material now as well, as you can tell. Now we're just like solving tiny little specific problems. Because I've taught you the whole of mechanics. So, yeah. Yeah, right, okay. So I'll write that down my list. That becomes very complicated, right? So there's two ways of doing buoyancy. There's the easy way, and then which is essentially a harmonic oscillator, and then there's a much harder way, which is what you're describing, which is actually taking into account the shape of the thing. Now you could use. I mean, it depends on what it is, right? You could use the collider boundaries to work stuff off like that. Now, what's going to happen is you're going to find out that it's going to be an extremely, extremely difficult problem to work out really complicated meshes and things like that. But you could estimate based on where the center of the mass is and work around that. So we'll I'll think about that before next lecture, and I'll see if I can find you a nice solution for buoyancy that does take into account more complex shapes rather than just like, oh, here's a harmonic oscillator. I may not have a good answer for you, to be honest, because here's the thing, right? Game engines, they're not really based on, when you've got these meshes and stuff, they're they're not real objects. We've got their point mass. Everything in a game engine is a point mass, and it's just a tiny point in space, and then we're just fleshing out a collider around it. And the game engine doesn't actually understand how much volume is in things. We just understand it like intuitively, but it's not actually true. It's not simulated. So when you try to start simulating things that don't actually exist within the simulation, that's when things get complicated. But there will be a solution to this. The problem is, and I'm sure that here's the thing: if you gave me 2 weeks, I'd come up with a really nice buoyancy simulator for you. But it's whether in 2 days I can give you a satisfying answer, because this is the type of thing where, like, you'd work hard on this for several weeks to try and get something that feels good. I may not have time to come up with a solution that you want to hear to this problem, but I'll think about it and we'll see if I do. Maybe I'll have a brainwave, or maybe it'll be simpler than I thought. But yeah, that's it's on the list. Buoyancy, that's going to be fun.